Yeah, thanks for inviting me to speak here. I have the exciting prospect of giving a talk about machine learning to a statistics audience, so please don't eat me alive. Hopefully this will be interesting. It's going to be, let's say, relatively high level with some gory details for the interested. Yeah, thanks for the introduction. This is not very much time series oriented. This is mostly to do with images and also text. So before I, okay, that's the right one. Before I get into any work or results, I just want to acknowledge that there's quite a few people in this team. So we're the biomedical imaging group in Microsoft Research, so we're up by the train station. What I'm presenting is a group effort, very much not only me. We have quite a few people, machine learning researchers, engineers, who are also lucky enough to have a radiologist who works with us part-time to help ground us in the realities of the data. So I'm going to talk about vision language processing and also radiology. So let's start with the vision language processing part. So a very quick introduction to vision language processing. So what we're trying to do here is learn an image encoder and a text encoder. I have virtually no mathematics on any of these slides, but basically both of these things are just a function that goes from either an image or a piece of text to some vector representation, usually, I don't know, 700 dimensional, something like this. These functions are deep neural networks. The purpose of the image encoder and the text encoder is basically go from this complex image to some representation which captures the meaning of the image, and similarly for the text. So how do people do this? Probably the most successful method for this is something called CLIP, if you've ever heard of it. It's called contrastive language image pre-training. The basic idea here is you start from a data set which has paired images and text. I think in this data set they're using images with captions crawled from the internet. Later on we're going to be using radiology images. What you do is you embed the text and the image into the same space using your encoder. So you're mapping them into this joint latent space that people say. And then the way you actually optimize, so you learn the parameters of these functions or these models, is you have what's called a contrastive objective. So I think I have a pointer, yeah. You basically have true pairs. So here there's the image of the puppy and its caption, and you want the representation of this image to be very similar to the representation of this text, but not very similar to the non-pairs. So within this batch of examples, there will be the captions of other images, and you want the puppy picture to not be similar to the caption of a cat or something like that. So you basically are trying to, you have this, people call it an affinity matrix, where it's sort of the similarity between everything in the batch. All of the true pairs should have high similarity, and all the non-pairs should have low similarity. That's your objective. Optimize this over the whole data set, learn the parameters of these models, and you get your encoders. So what am I actually going to do with these encoders? So one of the things you can do with CLIP, which is kind of exciting, is what people call zero-shot classification. So the historic traditional machine learning paradigm would be, I train an image classifier that tells me, given a fixed set of classes, which of the classes is in this image. If you have an image encoder and a text encoder which map into this space, you could theoretically take any piece of text, and here it could be a photo of whatever, and you could check the similarity of that piece of text with your image, and you could use that to classify your image, potentially detecting classes that you didn't even think about when you first trained your models, provided your text encoder is able to represent them adequately. So people say zero-shot classification. This is something that we do later on, where you could, for example, have an image encoder that takes an X-ray, a text encoder that takes in text, and include phrases like, I don't know, consolidation is present or pneumonia is present, and try and use that to classify your image for conditions that you didn't think about when you trained it. You can also use this as a good initialization of your models. So you could start with this image encoder, and then you could take a supervised data set. So here's a specific set of classes I want to classify, and continue to train this and use it as a good initialization. This is very common. You can also do interesting things. If you've seen the news recently, there's things like DALL-E, where you can start with a piece of text and generate an image. This model uses something like CLIP in the background because it's ultimately just about relating image information and text information. So that's vision language processing. Let's get on to radiology. So I have no idea what kind of background people in here have, probably better than mine in this, but nonetheless, let's talk about the radiology workflow. So a patient will be sent for imaging. The image will be taken. We're focusing on chest x-rays here. The radiologist will examine this image, potentially some other information, prior images, prior reports, etc., describe what they see in the image. They'll also summarize these observations into some kind of impression or conclusion. This report will then be sent back to, let's say, the referring clinician, and this will inform the care and treatment of the patient. There's many different places you could imagine vision language processing, machine learning, AI, etc., interacting within this process. What my team has been looking at for the last couple of years is the sort of middle part. This is the interaction between the image, the radiologist, and some text. So we're thinking about helping radiologists, basically. So it's not necessarily about the referring clinician, it's not necessarily about the patient. Our user here would be a radiologist, most likely. So what are the challenges that radiologists face? This is probably well known to most people, but there's an ever-increasing caseload. Radiologists are pushed to work faster or longer. There is severe understaffing across NHS, including radiologists. The task itself is intrinsically demanding. You can easily miss small findings. Interpretation can be ambiguous, especially in X-ray, where you're looking at something 3D but in 2D. There are known cognitive errors. This has been studied a lot in radiology reporting, where, for example, once you found something, you may stop looking for other things, maybe not consciously, but this can happen. So the result is there can be errors, patient care can be delayed, and there can be burnout in the workforce. Obviously, we would like to help. So how could vision language processing help in this milieu of issues? So one of the things we can do with these image encoders is help with the image understanding. So we could build image classifiers, help detect, maybe there's a pneumothorax in this image. We can also look at perhaps drafting a preliminary version of the report, specifically the findings section, which describes what is seen in the report. And you can also do things like, given an already written report, you could do additional peer review to perhaps discover inconsistencies between the image and the report. We've done some work trying to detect, for example, laterality errors. So the pleural effusion's on the left, but they wrote that it was on the right. So you could do things like, detecting errors, but then maybe also enabling the radiologist to maybe press a button that says, double check, did I miss anything? Almost like a spell check to see, are there any mistakes, which could help their sort of security that they've done a good job. So various potential use cases, overall trying to get to faster, safer, and easier work for the radiologists with presumed downstream impact on patient care, although that is to be determined. So how do we get there? What we've been trying to build is a radiology specialist vision language model. So this can understand images, understand radiology language, and ideally do some kind of image language reasoning. You could imagine a system like this where you give it this chest x-ray. You could potentially ask it a question, if that's a sort of a use case that people would be interested in, and it might give you the answer. The pleural effusion is in the left base, and we have our beautiful black box here. So some technical challenges here. The scale of the available multimodal radiology dataset. So of course, to begin all of this, we need paired image text data. The CLIP model was trained on probably billions of examples. We don't have that kind of data, so we have to make use of what we have. There's also radiology-specific nuances of language. A lot of the work in this area assumes you basically have an image with a caption, but a radiology report is much more complex than a caption. And of course, this is a high-stakes domain with very little room for error. It's not good enough to say, we have a 75% accuracy, have fun. You need to actually evaluate, is this model doing something reasonable? So what have we done? We've trained some models. So my team has been working on this data set called Mimic CXR. This is an open access data set if you're interested in this kind of research. It's sourced from a hospital in Boston. There's also accompanying electronic health records time series data, but just for now, we're looking at the X-rays with the corresponding reports. There's about 200,000 examples from around 50,000 patients in this data set. So what we're trying to do here is we're actually using the impression section. This is the closest thing to a caption that the image has, and we're trying to match it with the image. So I've taken the diagram we had before. Instead of pictures of puppies, we have chest X-rays with the impression section, and we train a model very much like you would train a CLIP model. I just want to mention that this is something that other people have also done. My team didn't invent this idea, so there's work from 2020 doing this, also 2021, various different improvements and nuances in all of these papers. And then this is a paper from my team, I'm here in the middle, from last year. So I also want to mention something, it's kind of something we added on in our paper, which is to do with something called phrase grounding. So the idea here is instead of getting a single representation of the image, so I have my image and goes into an encoder and I get a vector, what I could do is I could get a grid of vectors. So the idea would be you basically split your image up into a bunch of patches, and then you get a representation of every patch of the image. If you do something like this, it allows you to localize things. So now you can do your normal text image similarity, but you do it on a patch level. So you could have a phrase like enlarged cardiac silhouette. You compare its similarity with every patch of the image, and you could, I'll have a figure in the next slide, basically get a kind of heat map of similarity across the entire image to show which part of the image is most similar to this phrase. And this is something machine learning called phrase grounding. Note, you do need to change your training objective to actually enable this, because now we need these patches. But if you're interested in the details, I can point you to some papers. So here's an example. These are sort of our heat maps. You can see the granularity. It's not super high resolution here. I think it's like 16 by 16 or something. But we get this heat map of similarity. So you put in these queries, and you get the outputs in the image. So my team developed a benchmark for this, which is available on PhysioNet if you want to use it. It has about 1,000 image with bounding box and sentence pair examples across 8 different clinical findings, which were manually annotated and curated. So if you're interested in this kind of research, please use our data set. Okay, that was kind of the first paper. I think we're okay for time. So let's go back to this report. We noticed something. There are mentions of change. Large left pleural effusion is new, right effusion is new, maybe something is resolved or changed or is stable. This is very common. In fact, it's arguably recommended. So looking at previous images can improve interpretation and also enables you, especially, I should have mentioned, this is an ICU data set. So many of these patients are getting a chest X-ray every day. So it enables you to track disease progression and see, is this treatment working? Do we need to change? So what do you do about this? It can be a challenge. We also know that in this data set, about 40% of the reports actually mention prior images. So remember, we have 200,000 images for about 50,000 patients. Many patients have many images. So this is a problem because, remember, we're trying to do this image text matching. But if the phrase lung nodule remains unchanged comes up, and all of my images have a lung nodule in them, which is the right one? So this introduces an ambiguity. When we try and compute, this is our sort of affinity matrix. Model literally can't say which is the correct one, so there's some noise in our training objective. So what is the solution? Extremely obvious in hindsight. Why don't we use both current and prior images? So now we're going to try and compare 2 images with a phrase. You could extend this to more, but we only did 2 in this paper. So once you've done that, now something is unchanged here. This lung nodule is indeed unchanged. That means this is the right phrase. Resolves the temporal ambiguity, and it enables the model to learn that yes, these images do indeed have a lung nodule in them, and it is indeed unchanged. And what's exciting and enabled this work is that this mimic CXR dataset actually already has this image ordering information in it. There's a metadata file that tells you which of the patients are and what the orders of the studies. So we didn't actually need to get any new data. We're just using the data that already existed. So that was this paper we presented at CVPR, which is a machine learning conference this summer, which was all about extending our previous work to account for this temporal structure in the data set. Okay, this is where we get into the beautiful diagrams land. So just to go into some of the details, the challenge now is that we want an image encoder which can take 1 or 2 images. We don't want to assume there's always a prior image because that's not the case. And we want our model to still work if there's 1 or 2. The other thing is we don't want to have to do registration. So this would be basically trying to align the 2 images. So something that people do in the world of, for example, satellite surveillance, where they're trying to see how things are changing on the surface of the Earth, you can know, okay, these are exactly the same part of the Earth. So you can just overlay the images and feed it into one image encoder. We can't do this because chest X-rays, they could be rotated, there could be changes in the acquisition angle. So we don't want to have to register these images. We want our model to be able to take a current image and then a prior image, which could be theoretically arbitrarily rotated or slightly modified. The approach we have is a hybrid model, which is a combination of a convolutional neural network and a vision transformer. The CNN is extracting the patch level features, and then VIT, the transformer, is integrating the prior image information. We'll go through this on this next slide. Feel free to zone out if you don't know anything about machine learning, but if you do, you might be interested in this. So basically what we have here is we have our prior image, we've got our CNN. This is extracting these patch features. So this is where the story finished in our first paper. So at this point, you would do some kind of clip objectives. Maybe you aggregate these features. We'll have a text model here, and we can compare them. However, we want to include our prior images. So what we do is, if we have a current image, sorry, we always have a current image. I think this clicker is going a bit. That's better. So we always have a current image. We extract its features. We then have a pass through here. This is our final feature representation. So we always have some features from the current image. If we have a prior image, we pass it through the same feature extractor. So now we have our patch embeddings. Now what we do is we're trying to combine the images from the current and the prior. Our rationale here was that we're mostly interested in the current image. What we want to do is try and represent what's different in the prior image. So we include spatial encoding. This tells us our transformer where in the image we are, because we're about to flatten these into a line. We also include a temporal encoding that tells our transformer this is the current image, this is the prior image. We flatten and concatenate, so now we just flatten these out. We pass this through a transformer that has multiple layers of self-attention, transforms these. Again, we reshape them back into the grid. And now we call this thing our difference embedding, because it's supposed to capture everything from this image that's relevant to the current report that's not in this image. We concatenate these feature-wise into this grid. So now we have, theoretically, if everything's gone well, let's say here we'd have the representation of what about the current image has changed or is unchanged and is changed in that area, if that makes sense. So this is our multi-image encoder. There we go. Oh yeah, I just explained this. So we get the patch features, and then we do this feature-wise concatenation. Putting it all together, this is how we actually train it. So we have our image encoder that I just showed you. We get this image representation. We also have a piece of text. We have a couple of different objectives here. I'm just going to skim over these for now, but you basically get some representation of this text. So we turn this entire piece of text into some kind of little vector, and then we compare it here. We have global and the local contrastive loss is what I alluded to earlier, that you have some similarity between individual patches and pieces of text. So that's the basic architecture. And what is the impact? So our headline result here is basically that when you do this temporal aware pre-training, you do better, even given the same data set. So we have a task here, which I mentioned earlier, which is this zero or few shot classification. So you compare the image against a sentence embedding such as pneumonia is present or absent. This is an existing RSNA pneumonia detection data set. This is a single image task. You're just looking at a single image at a time. You don't need to use the fact that our model can take 2 images. We're just using the fact that it was trained with 2 images. And to briefly show you the results, this is BioVil and BioVil-T. These are the names of our models. This is our earlier model. This is the newer model. They're trained on exactly the same data. They have a very similar architecture, but because BioVil-T is able to use this prior image when it's available, the overall representation of the image is higher quality. This is what we take from this. What we can also do is enable new tasks. Now we have a representation of the 2 images, so we can ask questions about change. So this is another benchmark data set that we have released. So the objective here is we have 5 pathologies, and we want to classify them as worsening, stable, or improving. So this is to do with this pre-training thing that I was talking about earlier. We have an image encoder that can take 2 images. So for example, this is a prior image, is a current. This consolidation is getting better. We want our model to be able to classify that. So this is our benchmark data set. We have about 1,000 image pairs from 800 subjects, which was once again labeled. And the results, briefly, significantly better than prior work, although this is a relatively new task, so I'm not going to hold it against anyone. Part of the reason we released this benchmark was to try and encourage further work in this classification of progression, because a lot of people have done just diagnosis, like, is there a consolidation, yes or no? We think it's interesting to try and get into slightly more complex tasks. What we're seeing here is macro accuracy across these 3 classes. Overall, not amazing performance, definitely not about to deploy this, but certainly better than prior work. I should note pneumothorax is extremely challenging. one of the reasons we think this is because many pneumothorax cases, they're very, very small and quite difficult to see. And we're using, I think these images are like 508 pixels across. So we probably need to work with higher resolution images to be able to see the change in a pneumothorax. Great, we're doing okay for time. Another thing that I mentioned that you can do with these models is to try and generate a report. So this would be starting from your image encoder, train a text decoder to go from the image representation to a piece of text. This is a very common task in the machine learning on chest X-rays universe. However, one of the problems is because we know, like in this data set, 40% of these reports mention a prior image. If you just train from a single image, you're going to encourage your model to hallucinate change information because you're telling it, yeah, from this image, there's been a change, but it has nothing to base that, output on. So of course, we recommend using the prior image and also potentially the prior report. So what we have here is our multi-image encoders. This is our little feature concatenation. So you use the current image, the prior image, then you have a text decoder. You can potentially give it the prior report, and then it generates, for example, ideally the correct report. And of course, we have some tables with numbers where we show that this improves the quality of the reports using a variety of different metrics that I can tell you about if you're interested in later. But what we're showing is some ablations here where using both the prior image and the prior report improves across various metrics. We did introduce a sort of new one for this analysis, which is temporal entity matching. Basically what you do is you look at how the change words in the ground truth report correspond to the change words in the generated report. So evaluation of text generation is really quite complex, so that's why we have so many different metrics. But the idea here is that we're trying to check, is our model generating the word improving when it should be, or perhaps not. Yeah. So that's basically it for the results. So I just want to come back to where we started from. So we're trying to get to a useful vision language processing radiology. We can do image understanding, and image language reasoning. Of course, we are still very far away from useful models here, but we have been making various steps towards this. So we've been trying to improving the pre-training, so kind of squeezing more out of the data that we have, trying to build better medical image encoders. We've been building new evaluation benchmarks and releasing data sets. And I didn't talk about this at all in this talk, but something my team's also interested in is using large language models. We have a paper about using GPT-4 for radiology text processing. If you're interested, happy to talk in the break or anything. So with that, I'd like to thank everyone for their attention. Note that our models are available if you want to use them. We have code, we have these data sets. Once again, various collaborators and indeed extended team.
Questions. There's one there and then there's one there. Hi, great talk. Yeah, I have 2.5 a question. I'll start with the half first. So I think like when I was looking at the mimic dataset size, I mean like you're using BART, I guess pretend, which is pretend, but are you also using a pretend image encoder? Because I think it's quite tricky with such small sample size to train a vision transformer. So that's my half of a question. I guess you're using pretend encoder. And the other question, what I kind of find a bit counterintuitive is when you're using two image, for the current image, you are not using, I don't understand why are you not using attention for the current image as well? Because the natural reaction should be if you have the current image, then you pull in the key and value thing from your prior image, but you're not doing it, you're doing a pass through, which I kind of found difficult to understand. And the second question is that your sequence lengths are quite small because you're using the impression section. So what's the motivation of using transformer? You could have used a LSTM for that.
Yep. Okay. So starting with the half question, which I have already forgotten.
Pre-training. Are you using pre-training?
Yes, yeah, thank you. Yeah. So our CNN is ImageNet pre-trained.
Oh, right.
The vision transformer part is relatively small, so we do train it on this data set. I should note that we do. So the CNN starts with ImageNet, then we actually do image-only self-supervised training, and then we do this clip-style joint training. So it's kind of a long pipeline. Second question to do with
not using attention for
Yeah.
the current image.
So we are. I probably didn't explain it very clearly at the time. So basically, we have a pass-through for the current image, so we always preserve just the current image features because the report is corresponding to the current image. The attention is over the current and the prior images. So we actually concatenate them, and then we do self-attention across all of it. Yeah. We did experiment with not doing the pass-through initially because we thought we'll just ask the transformer to combine all the information. But we found because the current image is so important, adding that pass-through is quite helpful. What was the third?
And that is like your sequence length because you're using the equation section.
Yes, so
So what is the motivation of using transformer? Because if your sequence length are small, you could go ahead and do LSTMs and save some parameters and
yes, so just in case anyone online didn't get the repeat question, so why are we using a transformer instead of an LSTM given our sequence length is relatively short? So there's two answers to that. The first one is we're also using a pre-trained language model. So we're reusing some BERT model, which we also do some domain-specific pre-training. The second answer is since we worked on this, we've actually moved to generating the findings section because we think that's a more appropriate thing to do because that's more fully based in the image, and the finding sections are actually longer.
thank you.
Thank you. That was a really excellent talk. I'm an intensive care physician, and radiology is a relatively precise art, but intensive care patients produce the worst images in the hospital, produce slumpographs. And so I feel really sorry if you had to work with that data. I'm sorry on behalf of my colleagues. But the question I have is, a lot of the features on our slumpographs are actually artifacts because our patients are so rotated, you get bits of the spine, which looks like consolidation. And those features won't be processed in terms of the text because the radiologist knows that's the spine and won't necessarily comment on it. So how are you going to allow for sort of artifactual features being interpreted as genuine pathology when those features aren't actually encoded in the text? Do you have to rely on highly curated data or mimic to do that? And then the second sort of question is, have you also used CT images, or not the images per se, but the reports? Because often in the ICU, we have chest x-rays and then CTs quite soon afterwards. And there's often a degree of interpretation of the chest radiograph interpreted by the radiologist, but the CT is kind of definitive. That's the gold standard ground truth. So could you augment your text encoding with an additional bit of data, essentially?
Yeah, if you have a CT data set we could use, that would be great. Yeah, so to answer your first question about the ICU and the quality, yes, it is. Okay, so the MIMIC team, very commendable that they have shared this data. This is a consistent challenge that we have, that we're trying to work with a very messy data set. Like even things like, because these patients have so many repeat chest x-rays, sometimes the report doesn't mention things which would have been mentioned in a prior report. So we have this kind of missingness thing. So yes, indeed, the technical quality is sometimes commented upon, and now that we're trying to generate the findings section, they will sometimes say patient is rotated or like motion artifacts, that kind of thing. So in theory, that information is in there. In principle, I think what we do find is that because we're trying to match with the impression section, our model ends up being pretty good at extracting the features that are pertinent to that. So, you know, the key findings, but it doesn't necessarily pick up on maybe the more nuanced aspects of the image. So this, yeah, the data quality is really quite an issue in all of this. I'm trying to make sure that like you're not feeding it noise. There's also, you know, these models pick up a lot on association. So for example, something part of the team has been looking at is the association with like pneumothorax classification in tubes, because the model can see a tube. It might not be able to see a real pneumothorax, but maybe there's a pneumothorax. So there's some of these challenges in the data set are quite bad.
But that tube could be for fluid as well, so.
Yes, exactly.
So, yeah.
Yeah, so there's and then regarding CT, this is very much a data set availability thing. So MIMIC is an open data set. To my knowledge, there aren't any open CT data sets of the same scale, but we would love to get into looking at CT reporting. Also, it's more structured, which could be beneficial.
Thank you very much.
Any further questions?
Thank you, great talk. I have a question, but I'm not an expert in this kind of field. But I know that, for example, for brain imaging, people look at scanner differences. Is that something that you have in this data set, or you can tackle with this data, with this kind of approach? And is that a source of, I don't know, changes in your results?
Yeah, so I think, I'm not sure about scanner differences, but because this is an ICU data set, there's a lot of AP or PA images, so basically which direction was the patient facing when the picture was taken, or are they standing up, lying down, sitting, and that, as the person asking the question, that can have quite an impact on the interpretation. So for example, if a patient is lying on their back, the fluid in their lungs looks different to if they're standing up, gravity and so on. So like those can have an impact. We're not explicitly feeding this information to the model. I think in AP versus PA, you can kind of tell just by looking at it. But yes, this would potentially be a source, especially if there's some alignment, and like we do find this, like patients who are sicker are more likely to have an AP scan. So there might be some association that our model picks up on between, some basically spurious feature and the fact that they have all of these other findings. So yes, it's definitely a concern. We haven't characterized the extent to which it's impacting our results though.
Thank you.
Thanks.
Thanks, that's really interesting. So I've got a kind of standard statistician's question, which is about sources of variability. And, so can you get a sense of, physician to physician variability, site to site variability, temporal variability, and how you would attempt to deal with that if you were actually rolling this thing out, either in an initial training phase, or how you would design a rollout in a way that enables you to get at some of those things?
Yes, so in this data set, we don't have any information about who wrote the report. So we have no way of knowing, is there a kind of physician level impact? Similarly, this is a single hospital. So we're kind of constrained in that regard. I think I have seen some work where they have tried to take sort of individual radiologist style into account. And certainly, so something that Theo, who we work with, we look at a lot of these reports with her. These are from the US. She works in the UK. You can clearly tell there are differences. And I've worked with some other US data sets, and you can also see that there are differences. So I think this is something, obviously it would depend a lot on what exactly are you trying to build and how are you trying to use it, that you would potentially something, an idea that people have with these models is you sort of try and build a general purpose model, and then if a particular hospital wanted to use it, they would then fine tune it so it maybe generates the style that people are used to. I don't know if that.
Yeah, exactly. So I was kind of interested in how you would design those studies, and ideally you don't want to do it one hospital at a time. More structured. If I start thinking about that as a design problem, I have no idea.
I think for something that we have looked at, so we do have access to a different data set that isn't Mimic, and something we've noticed, so we're trying to generate reports, and we thought about using the indication section, because this basically tells you something about the patient's history, or like, why is this image being taken? So we thought, okay, maybe that's going to help improve the quality of the report that we're generating. And we found it had a really big impact when you then change which center you're reporting from, because the indication was basically a proxy for which center it is. And this is something, not this work, but prior work I've done predicting postoperative hypertension. We've discovered the model is amazing at picking up any of these spurious features, like anything which has to, like we had data from 2 hospitals, one of them was a trauma hospital. Those patients had much more postoperative hypertension, but the settings for their ventilators were slightly different. And so when we attempted to figure out what features were important, and those were really, really informative. So yes, I guess this is maybe like a failure story that we discovered that these things really matter, but it certainly, if you wanted to have something that works in a specific hospital, you really want to get data from that hospital. And ideally, if you have multiple centers, you can then, you can feed it into the model in different ways, and this is something people try and do. There's a whole area of like trying to account for potential sources of sort of bias in the model. But for now, we're kind of just at trying to generate something that is clinically remotely useful. Thank you.